Chemical equilibrium. Historically speaking, and I think I mentioned this before, the reason we do kinetics first now is because it helps us understand chemical equilibrium. But historically speaking, the work on equilibrium and kinetics occurred at about the same time. Arrhenius proposed his kinetics equation in about 1880, something like that. And equilibrium was already hit the ground running as it was introduced in the 1860s. But the full treatment of kinetics required further development of thermodynamics. So it really didn't get a good running start until the first of the 20th century. Chemical equilibrium refers to the state of a system. In other words, kinetics is more a action driven, whereas equilibrium is where the system ends up when it's finally stable. Now, how does it get there? Well, we know that kinetics involves reaction rates, we looked at the collision theory, right? So on the molecular level, collisions are occurring at unbelievable rates. In other words, and not all of them, of course, result in a reaction, but you've got what I'd say is furious activity at the molecular level. What we see macroscopically on the surface is just changes in reactant and product concentrations. So it's not obvious to us what's happening underneath unless we understand kinetics. So it looks like once we've reached equilibrium, everything is perfectly stable. But at the molecular level, even when things look stable from our perspective, microscopically, you still got a dynamic situation where the forward reaction is balanced by the reverse reaction. Okay, so we're going to take Haber-Bosch as our example. And yields to ammonia. Oops. The oxygen come right along. Okay, so 2 and 3. Here we go. And this graph illustrates what we see as the reaction progresses. And we've already looked at that in terms of reaction rates. But in terms of concentrations, what we see is that before equilibrium is reached, when we start, there's no ammonia. There's just hydrogen and nitrogen in these stoichiometric ratios. But as we progress, the ammonia concentration increases and the reactant concentrations decrease until we reach a stable point at equilibrium. Now, we express that in terms of concentration. At equilibrium, you'll have a certain concentration of N2 remaining, a certain concentration of hydrogen remaining, and we'll have some ammonia in that solution. But you still got the reaction happening at the microscopic level. It's going this way and that way. So as you build up ammonia on this side, you have more opportunity for it to decompose and produce reactants again. So what we're saying is that the forward rate of reaction, and we might say like this, the rate or rate F for forward and the rate reverse. Those two rates have to balance in order for equilibrium to be established. Now, these rates, while they're fundamental to establishing equilibrium, the rates can be anything. It just depends on the reaction and the conditions, right? Temperature is a large factor. Pressure for gases is a large factor. So this reaction may occur very, very rapidly this way, and maybe not so fast the other way. But eventually, their overall rates, forward and reverse, balance. We see that as the product builds up, the reverse rate increases because you have, as we learned in kinetics, if you have a starting concentration is increased, then you get an increase in rate, right, based on the rate laws. And of course, as these reactants decrease, you're going to get a decrease. Now, if we were to write the rate law here, the rate in that direction would be equal to some constant, and then into concentrations to whatever its order is, and then to its order. And then this would be the forward rate, and then the reverse rate would be its, this is, I probably should have put a K up here. That would have been more accurate. So the forward K and the reverse K are different. But the reverse K is dependent on ammonia. And let's just say that's P. Okay, so you have two different rates. And it's dependent upon the concentrations of forward rates, concentrations of nitrogen and hydrogen. Reverse rate depends on ammonia rate. But when those two rates balance, when this one is equal to that one, then you have equilibrium. All right. So let's consider, for example, this reaction where we react water with carbon monoxide and we get hydrogen gas and carbon dioxide. Since we understand what it takes to modify the rate of a reaction in terms of the rate laws, what would happen if this were an equilibrium situation? In other words, we're established equilibrium where we have enough hydrogen and carbon dioxide formed that its reverse rate equals the forward rate. So we're at equilibrium. Now, what if we change the concentration? Say we add hydrogen, water or water vapor to the flask. How will that change the concentrations of the other reactants and products? Okay. And I think these are all gases. Yeah. Carbon monoxide. And this gives us hydrogen gas and carbon dioxide gas. Okay. We're at equilibrium. Now we're going to add some water vapor to that reaction. What should happen? If we write the rate law for the forward reaction, then we have concentration of water to its order and carbon monoxide to its order. Then if we increase this amount, the forward rate should increase. Well, it increases until the forward rate equals the reverse rate. See, let's make this P and make this Q. So we're going to stress the system. It's at equilibrium. We're going to add that amount. So we know that the forward rate is going to increase, but as we lose this and increase that, now the reverse rate increases, and eventually they balance again. We reach equilibrium. I just introduced you to Le Chatelier's principle, which we're going to investigate in our lab next time. We'll talk about that in more detail at the end of this chapter. If we were to add more hydrogen, you would see the reverse rate increase until we get enough water and carbon monoxide produced so that the forward rate balances the reverse rate. You could just as easily say, instead of adding hydrogen, we would remove. If you remove this, now the reverse rate decreases. And it's not going to balance until some more of it is produced. The forward rate now is dominant until we reach enough hydrogen to balance the reverse rate. So you can get similar effects to adding water by just removing products. Adding reactants, removing products, you get a similar effect. Okay. So I mentioned the math for understanding equilibrium is much simpler than it is for reaction rates and kinetics. So that's one of the reasons that this law of mass action, we call it, was developed before kinetics was fully fleshed out. It was proposed by a couple of Norwegian chemists, Waag and Goldberg. They were related by marriage, but they worked together in 1864. So that's about 20 years ahead of Arrhenius equation. It's nowadays, when we teach these topics, we use language that we're familiar with. But in their day, they used funny words. They meant something to them. And they call them affinities that drive chemical reactions. Right? That doesn't mean anything to us. So what they were after was they wanted a mathematical description of the equilibrium process. What does the system look like at equilibrium? They called what we call kinetics, they call it chemical dynamics. And equilibrium was chemical statics, those are valid terms. They're more commonly used in physics. Like statics is what you first learn in physics. Things are supposedly stuck in place, like levers, where you put something on this side, something on that side to balance it. There's no motion. It's just balanced. We call that statics. Whereas dynamics, like circular motion, planets orbiting the sun, would be a dynamic situation. But in chemical terms, dynamics is kinetics, reaction rates, and statics is equilibrium. And they were working with solutions. So they naturally expressed the reaction rates, the reactants and products in terms of their concentration in solution. And that's typically molarity. And you can even express gases in terms of molarity. You just have so many moles of gas in a liter of space. And that's where the square brackets come in. When you see a term in there with square brackets around it, this is equilibrium concentration in molarity, moles per liter. If you see parentheses, this is non-equal. We will use those later on. It's coming pretty quick. The other way you can express, especially where reactions involving partial pressures of gases, we can also express that in terms of pressure. So we just say pressure of whatever that term is. And this would be the partial pressure of the gas. Now, when we write the expression, and I'm going to show you the how we derive the expression in just a minute. When we write the expression in terms of partial pressures, all of the terms in the equilibrium expression have to be pressure. Whereas if we're talking about solutions or gases in terms of molarity, all of them, it's either one or the other. We don't mix them. Okay, so when we have this equation, this generic equation, where we're reacting coefficient of small a with A and small b with B, and then we have an equilibrium situation with C and D, then once we reach equilibrium and we've determined the concentrations of each one of these reactants and products, we write the rate constant, and we typically give it a large K rather than a small k. Small k's we use for kinetics, large K for equilibrium. Then we put the products in the numerator. And what's easier about this, about equilibrium as compared to kinetics, is you derive the equation from the balanced. You derive the equilibrium equation from the balanced reaction equation. So the superscript, the power, is coefficient. And similarly for any of the other products. And then in the numerator, we put the reactants. Now, I'm not sure why they did it that way, but it's standard fare now. What we can see from this is if we have a very large value for K, that means at equilibrium, you have lots of product and not very much reactant left because of the quotient effect. We have lots of product, very little reactants, gives you a large K. And if you have lots of reactant left and very little product for that reaction, then you have very small K. And this is called the law of mass action. Now, the other thing is, since we've got units here to the powers, and the powers can be anything, whatever the balanced equation tells you are the coefficients, those are the powers. If we try to follow the and present the K in terms of unit concentrations, well, if we had molarity, say 1, 1, 1, and 1, and these were all 1, 1, 1, and 1, then it would be there would be no units because it'd be molarity squared divided by molarity squared. No, it'd be unitless. But if we had values in here, like 2, 10, 4, and 6, you'd have some weird units. So typically we leave the units off. As long as we know how it's derived, and that's important, and we're careful with our calculations, then the units don't present a problem. But if you look up K values for any reaction in a reference manual, all you'll find is what were the base units when the reaction was investigated. Is it molarity? Is it partial pressures? And that's as far as they'll go. They won't put other units in there. Okay. So we're going to need certain rules. If we have to say multiply, say we're combining equations. We did that last semester, didn't we? Hess's law. We combine equations. Well, if you're going to combine equations to get an overall, and you want to know what the K is for the overall reaction, then you need to know how you treat the Ks for each individuals that you add together. So if we have to modify an equation in order to make the result come out correctly, then we need to know how does that affect the K. That's what we're after here. So first one is reciprocal. Right? If we have to write the reaction in reverse, what does that do to the K value? Well, it just makes the reactants products and the products reactants, which means this flips. And that means that the revised K is now K to the minus 1. We invert it. Okay. If we have to multiply by some value out here, right, multiply the whole thing through by X, what does that do to this? Well, that X is multiplied by each one of these, correct? So that would change each one and give it an X and an X and an X for each one of those. Okay. Then what we can do is we can factor out the X. If we have X by each one of these powers, that's the same thing as writing, is leaving these coefficients in place. And multiply the whole thing by X. So that means now that it's K to the X power. If you multiply a whole number through your entire equation, then the new K is K to that power. Okay. As long as you don't change the temperature, then the K is a constant. You can start off with any concentration you want here or there. Once it reaches equilibrium, then the expression of those values is equal to that K with a constant temperature. If you change the temperature, then the K changes. That's why we call it a constant. Let's see. Now that's the equilibrium constant. As opposed to equilibrium position. The equilibrium position is actually an expression of actual concentrations of the reactants products when you reach equilibrium. So if we start off with a very large amount of A and B and no C and D, you'll end up with less of A and B and some C and D. And the equilibrium expression will be a constant. And those values are the equilibrium position. If we start off with, say, less A and B, and we get some C and D, then we're going to have a smaller amount of A and B, and probably a smaller amount of C and D than we did with our first example. That's a different equilibrium position, but it gives you the same constant. Okay, that's a fine distinction there. It's like we're splitting hairs, but they are different. Okay, I just used a simple K here. If we're not specifying any special conditions, then we just say KEQ, equilibrium constant, or just K. And usually the K equilibrium implies molarity as your concentrations values. Water dissociation, and we're going to talk about that in more detail when we get to acids and bases. But water dissociation constant, we reserve KW for that one. Acid dissociation. Right? If we have an acid like acetic acid, what's it going to do in solution? Well, it's going to dissociate into protons and the acetate polyatomic ion. So there you have the possibility for another equilibrium situation. And that expression would give you a Ka. Okay. And like I said, we're going to get into more detail when we get to acids and bases. That's just to give you a flavor for what we're talking about. Solubility product is like that. And that's like, let's see, silver chloride, say. Remember, I think it was first semester. We talked about solubilities. When you double replacement reactions produce precipitate. Okay, and we at that point we said it's either soluble or insoluble. And I hope I mentioned the fact that there's a continuum between the two, right? So it might only be slightly soluble. Well, silver chloride is an example of slightly soluble compound in water would be in equilibrium with silver ions and chloride ions. Now, they're not very, most of it's here. Very little of it is here. Okay. But that brings up the other rule regarding this expression. If any of these are solid or pure liquids, we don't put them in the expression. Why? Because their concentrations don't change. Right? So, actually, that's not true. It goes from solid into these in aqueous solution. So in this expression, that would be left out. It would only be silver and chloride ions and nothing in the denominator. It's a product. That's why we call it solubility product. It's just these here, and that's a solid. Okay. So when we write these equilibrium expressions, we look for concentration values like molarity or partial pressures that can change during a reaction. And we also look for solids and pure liquids, and if they're there, we don't use them. It's like they don't exist as far as equilibrium is concerned. Okay, formation constant is another one, and we get to that one much later. So I won't bore you with the details right now. And if we're using partial pressures, then we call it Kp, K sub P. There are some others that we could bring up, but there's, we're not going to deal with them in this course. So, why clutter your mind with them? Okay, so here's our Haber-Bosch equation. And we have two possible expressions for equilibrium. One in terms of molarity and the other in terms of partial pressure. Okay. And you'll notice that the first one, partial pressure, uses the same set of coefficients as powers. The only difference is the expression of how we determine concentration. Is it partial pressure? Is it molarity? Now, obviously, when we use units of measure for partial pressure, say atmospheres, that's going to give us a different value when we calculate it as opposed to molarity. So the Kp and the Keq are not going to be the same numbers. And it's important that we know the units that we start with. All right. But they are related. These two are related, and they're related in a subsequent slide. So if we have equilibrium partial pressures for these gases at any given temperature, and we're not specifying it for our purposes here, but our concentrations are expressed in atmospheres, then all we have to do is take those values and plug them into the mass action equation there, and we get that value, 3.9 times 10 to the fourth. Okay, what does that tell you about equilibrium? Well, it's a very large number. So at equilibrium, you should expect a partial pressure of ammonia gas to be very high as opposed to nitrogen gas and hydrogen gas. The equilibrium lies to the right with these values. Now, we don't know what the temperature is. Right? If the temperature, in fact, I know that this reaction is exothermic. So if we increase the temperature to a massive amount, then, and I'll explain this in more detail later, you're going to get a shift in equilibrium to the reactants. So this must be at a very, very low temperature, which means the equilibrium expression favors products, but at a very low temperature, you're not going to get much reaction. So the equilibrium position is not favorable for an industrial production of ammonia. All right, that's not going to mean a whole lot right now, but it will. I'll explain it later. Okay, here's how we relate the two. Kp then is the K, and we just use K there, but I'm going to say Keq. And we need the gas constant, we need the temperature, and we need the change in moles of gas in the reaction. So if we're starting off with nitrogen and hydrogen to yield ammonia. Oops. Great. What's the change in moles? Well, delta, unless otherwise specified, means final minus initial. So the final number of moles is 2, minus the initial moles is 3 plus 1 is 4. So that's a minus 2. That would go up here, minus 2. Okay. So instead of RT squared, it's RT to the square root. That's what that means. A negative power is a root. And R, since we're, let's see. Right, since we're dealing with pressure here, then we need to have a pressure term in R. So we would use 0.08206 liter atmospheres per mole K. And that should be in useful information. It's not like you have to memorize it. Just know how to use it. Okay, so here's our example. If KP, we determine KP to be 3.9 times 10 to the fourth. And then if that temperature is 35 degrees Celsius, which is a little bit below body temperature, right? Body temperature is what in Celsius? 37. 37, stick it in your formula, 37 comes out to 98.6. Exactly. Okay, if we say KP equals 3.9 times 10 to the fourth, and then we plug in our other values and solve for K then is 2.5 times 10 to the seventh in terms of molarity. All right. Now, we mentioned when we were talking about catalysts in our last chapter, we mentioned homogeneous versus heterogeneous catalysts. We can use that idea for homogeneous equilibria versus heterogeneous equilibria. Homogeneous equilibria involves the same phase, only one phase. So the Haber-Bosch process is homogeneous equilibrium. If we're in an aqueous solution where we have this hydrocyanic acid dissociating, or actually it would be ionizing, into hydrogen and cyanide ions, they're all in aqueous solution, that's homogeneous. Heterogeneous would involve different phases. So this potassium chlorate decomposing into potassium chloride and oxygen gas, which, have I told you about that? We used to mix up potassium chlorate in solution, concentrated solution, and dribble it on the floor, and it would dry to a white powder, but it's so small you couldn't see it. And then the TA or the professor would come walk through, step on it, go pow, because pressure activates it. It would decompose into potassium chloride and oxygen gas, and the oxygen gas was the pop. I'm not saying you should do that. That's heterogeneous equilibrium. And the electrolysis or the decomposition of water into hydrogen gas and oxygen gas is also heterogeneous equilibrium. Now, in these cases, which term would be used in the first one? Right? KEQ for the first reaction would simply be that. That's it. Because you've got the rest of them are solids. So that's the only equilibrium, the only term in the equilibrium expression. The second one would have hydrogen and oxygen in it. Think. Yeah, two. So that would be for the second one. But we wouldn't use water because it's a pure liquid. And technically, there's no way to calculate its concentration anyway. Solids are kind of obvious, their concentrations don't change because they're not in solution. The pure liquids are a little touchier, difficult to the concept to understand that, but we don't use either one in the expressions. Oh, I already did that. Okay, and I already mentioned this one earlier also. If the K is much, much larger than 1, that means the equilibrium favors products because they're in the numerator. And if the equilibrium lies far to the right, and that's another, when you say which direction is the equilibrium going to shift, or which is preferred, right or left, those terms don't mean anything unless you've got a balanced equation to reference. Because I could write the same reaction, I could flip it, and now your right doesn't mean right anymore. I mean, it should be left. So when you say right or left, reference a balanced equation. Okay, just a word of warning, especially when we get into that lab and you have to answer questions. That's going to say, which way does the reaction shift? If you say left or right, be sure that you're referencing a balanced equation. And if that K is extremely large, then the reaction essentially goes to completion with very little reactant left over. And vice versa, if K is very small, then the reaction essentially doesn't happen. No significant extent for that reaction. So if equilibrium lies to the right, the value of K is large. Now, your textbook might say if it's just greater than 1, and that's what this says. I like to say large, much, much greater than 1, because when you've got powers in your expression, there's no way to tell if it's going to be exactly 1 if there's equal amounts on both sides, right? It may not be 1. But if we say it's much, much larger than 1, then we're pretty safe in saying that the reaction lies far to the right. Or if it's small, it lies to the left. Okay, I mentioned parentheses. Using parentheses is a non-equilibrium expression of concentration. When do we use those parentheses? When we're trying to determine which way our reaction is going to shift when we first put things together. When we put a certain amount of reactants together with products, it may not be at equilibrium at that place, but we know the concentrations we start with. So we want to use the equilibrium expression, the mass action equation, to determine which way is it going to shift with the starting position. Is it going to go to the right? Is it going to go to the left? That's important for solving problems later. Okay, so we simply use the same expression, only now we call it Q. And we would have parentheses with our former equation. We would have C and D and A, B, and we would have, it would look just like it did before, only now, instead of equilibrium concentrations, we have starting concentrations. And then we get a Q. Well, we know what the K is for that reaction. So we compare the Q to the K to see which way it's going to move. Okay. Well, obviously the easy one is if your calculated Q comes out to be equal to K, then you're already at equilibrium. You've set it up as an equilibrium mixture. But if Q is greater than K, what does that say about this reaction? If Q is greater than K, that means you've got more product than you need and not enough reactant. So it's going to go shift to the left. Okay. And vice versa. If Q is less than K, then you don't have enough product and it's going to shift to the right. Okay. All right. Simple enough. Okay. Now we're going to do some sample calculations. All right. Okay, for this reaction, why don't I go ahead and write it up here because of the way I like to work these problems. And it'll become obvious in just a minute. There's aqueous and SCN minus. We're going to do this reaction when we come back and do our first lab. And this produces the complex ion in a solution. And this ion is brick red, right? You put these Well, this has a slightly yellow color. This is colorless. When you put them together, you get this brick red. It's in solution, but it's a complex ion formed from these two. And K F, the formation constant, would be an expression of this one. And we would write the expression Kf equals this ion in solution. Since it's aqueous, it will, oops. Plus, there we go. And this is balanced with 1 as coefficients. There we go. All right. So for this first one, we're given 6 molar iron 3+ and 10 molar thiocyanate ion are mixed at a certain temperature, and at equilibrium, the concentration of this ion is 4 molar. Okay, so well, I stepped over a little. I'm going to have to shift just a little bit to the right. Let's put this over here as thiocyanate. This is our iron. Okay. I'm going to build a table. It's called an ICE table. ICE means initial concentrations, change, and equilibrium. Okay. So initial concentrations of iron is 6 molar and thiocyanate is 10 molar. So we've got 6 molar here, 10 molar here. I mean, only 1. And nothing here because we started out, that's our starting position. That's why I like to write out the balanced equation, and then I can use it to position concentrations. At equilibrium, the thiocyanate is 4 molar. So at equilibrium, here we have 4 molar. Okay. What kind of change was required? Well, we had to add a concentration of 4 molar there because that's 0. Okay. And if they're 1 to 1 to 1, how much do we have to lose on this side to get that side? Well, for every 4 we get over here, we lose 4 here. Right? And we lose 4 here because the ratio is 1 to 1 to 1. Okay, so now we subtract those and we get 2 here and we get 6 here. Molar, molar. Now we know our equilibrium concentrations. And we can calculate, let's see, thiocyanate would be 4. I'm not going to put the molars in here. And this would be 2. This would be 6, which would be 4 divided by 12, right? 4 12s, that's a third, right? 0.333. That's our equilibrium constant for this reaction using our ICE table. Let's see what my animations do. I can't remember what I did with those. Yeah, there it is. Okay, finish it off. There we go. So we've determined the K for this reaction at a given temperature. They didn't say what the temperature was, but whatever it is, that's our equilibrium. Now we can use that information. If we change any of these values, we can use them, and this determined by that experiment to solve another problem, now that we know what K is. So here we have our second trial. Okay, so let's make room here. I'm gonna leave that K in place right there. And we're gonna change this to initially 10 molar iron. It's initially 10 molar iron and 8 molar thiocyanate. So we're giving it a new equilibrium position. What is the concentration of this one? So if we're starting off with this initial concentrations here and we're still 0 there, this is a whole new experiment. Okay. Okay, we're not told what the let's see, equilibrium concentration of this one is. That's what we're after. Okay. So we can tell we don't have to calculate the Q to know which way this reaction is going to go because there's no product. It has to go to the right. So this is going to produce some amount here. Right. That's our algebraic placeholder. And we're going to lose that same amount here. Like that. So this is going to be 10 minus X. This is going to be 8 minus X. And this is going to be X. And we set it up so that if we solve for X, that will tell us, that will answer the question. Because that was the question. That's what we wanted to know. All right, so if I put those values in here, in this expression, I'm going to have to stretch it a little bit here. Let's do this. Let's do this. So the first one is going to be 10 minus X. Second one would be 8 minus X. And this is going to be X. Oh, wait a minute. No, X is on top. Sorry. My mistake. X is on top. 10 minus X. And that should be square brackets. 8 minus X. There we go. So now we have to solve for X. Okay. Everybody's had algebra, right? You know what this is going to give you? A quadratic equation. Right. Okay. There are ways around that sometimes. If the K is extremely small, then we can approximate. But this is not a very small number. It's only a third. So we might have to use a quadratic equation. Okay, let's go. Come on. There we go. So let's see if I set it up right. Let's see, K equals X. Yeah, set it up right. Then what you have to do is resolve that equation. So this expression becomes 80 minus 10x plus x squared. And then we bring this over here, multiply it by that, and that gives us x on both sides. Now we have to, how do you solve a quadratic equation? Everything's equal to 0. Okay, everything has to be on the same side and 0's on the other. Then you can use the quadratic equation. Now, when I was using it every day, I could remember it, but I have it on the back of my calculator now. So we would solve, our x then would be minus b plus or minus square root of b squared minus 4ac all over 2a. And if we resolve this thing, we should end up with 0.333 x squared. And it's important that you set it up with x squared, x, and the constant in this order, because this is A, and then that's B, and then that's C. and then plus 26.64 equals 0. And then we will put, this is B, so this term goes here, right? It's a negative. A negative value goes there, then plus or minus. Then we put that negative B, it's squared, minus 4 times this value times this value. And underneath that root, then we take square root of that term, and then we add or subtract it. And we get 2 values. Then you have to decide which one is realistic, right? If we look at X mathematical solution X 15.99, can that be? No, it can't. Because you're only starting off with 10 and 8 here. You can't have 15 there. So you throw that one out. And the other one is the one that makes sense. 5 and 5 and 5. Okay. So the concentration of the iron thiocyanate ion is 5 molar. Okay. That's the long way. Now, there are some equations and some solutions where you end up with 3rd, 4th, 5th, 6th power. Right? They might have, I've seen, what's the next quadratic? Cubic equation has an x cubed in it. And there is an expression for solving a cubic, but it's like this is huge. So when we get to that point, if you go past quadratic, then it's simpler to use another method called the successive approximations. And we'll go through one of those and I'll show you how it works. And if you've got a computer that's set up to solve problems like that, then that's very often, you won't even do this one. You just plug in your numbers and let the computer do the crunching. But that's one solution. Okay. If we change the parameters now, we have 6 and 6 here. Then we go through a similar process and solve our equation, and we end up with x equals 3. Well, it's a new position. If it's now 6 and 6, notice we have smaller amounts here, so we should expect to have a smaller x. Instead of 5, now we have 3. Okay, when we reach equilibrium. Because now the rates, the reverse rate is established quicker, well, not quicker, but at a lower concentration. Okay. So when you solve equilibrium problems, you need a balanced equation. That's first and foremost. Same as stoichiometry. You got to balance the equation. And then you generate your law of mass action, because that's fundamental to solving an equilibrium equation. Then you use your ICE table. Initial concentrations. If necessary, calculate the Q. If any of your terms, initial terms, are 0, then you know instantly which way it's moving. If this is 0 and that's something, it's got to move this way. But if you're given values for all your terms, then you have to calculate the Q and say which way is it moving, because then that tells you which is minus and which is plus for your change. Let's see. And then you put your X in wherever, if possible, wherever solution for the X will give you the answer to your problem. It's not always the case, but if possible, set your X equal to the answer that you're looking for. And that saves you a step in calculations. Then you substitute your values into your expression and solve for the unknown. Okay, here we have different possibilities. I'm not going to take up your time doing these. You got plenty of practice in your review documents. You work on them, and we'll review them next time we meet. So for the first one, those values you should get, let's see. Find the equilibrium concentrations for all species. Okay, so we're actually given values for each one of these. So here's what it would look like. I'll leave that there. If you're actually given values, say 9 here, 5, and 1. Then you would have to calculate the Q and compare it to 0.333 and see which way it's moving. And if you did all that, then the equilibrium concentrations should be those values. Okay, just to check yourself, if you want to go back and do these, those are the values you should get. So that tells me that the first one moves to the right. The second one, 3, 2, and 5, moves to the left, because you start off with 5 and you end up with 4. And then the third one, you start off with 2, 9, and 6. You're at equilibrium. So if you calculate the Q for that one, where you have 2, 9, and 6 here, you should end up with 0.333. Okay, so I'm going to clear the board. I think I have the quadratic equation in useful information too, in case you need it. It just depends on which method takes the least amount of time. Usually the quadratic is quicker than successive approximations. But if you're faced with a, well, actually, if you're faced with cubic or higher, then successive approximations is the way to go. But I'm going to show you in a few minutes estimations for situations where the K is very small. And that simplifies the equation so you can solve it. And then you do a calculation and see if you're within a certain percentage. And if not, successive approximations would be your next step. So we'll get there in a minute. So 2 mole sample of ammonia is introduced into a 1 liter container. So what's its concentration? 2 mole per liter, right? So there's our balanced equation. Well, no, that's not balanced. We need a balanced equation. So if we've got, what does this look like? Looks like the reverse of the Haber-Bosch. Okay, so this would be 2, this would be 3. That would balance our equation. And if you start off with 2 mole per liter, the initial concentration is 2 molar. Right? Okay. No, that's not right. Only 2 significant figures in that. There we go. And nothing here, nothing here. So we know it's going to go that way. At equilibrium, 1 mole of ammonia remains. Did the volume change? No. So 1 mole of ammonia means 1 molar at equilibrium. So we know now we have 1 molar here. So what was the change over here? Well, if we lost 1 molar, that would explain this outcome. If this represents 2, what represents 1? Half molar. Half molar for his, because it's 1 to 2, this should be plus 0.5 moles. And this would be 3 times that. Okay, this is molarity. Okay, so now we have 0.5 and 1.5 there. So we can calculate the K. Okay, we have to balance the equation first. Oh, it was expecting me to do it anyway. But we'd have to write our equilibrium expression as N2 to the first power and H2 to the third power, and then ammonia to the second power. And N2 is 0.5 to the first power and 1.5 cubed over 1 to the second power. Okay, and that should come out to 1.69. Okay. So far, so good. Start working problems and then bring your questions back. Okay, and you can contact me over the holidays. I mean, if you have some spare time, you want to work some problems and you hit a snag, just shoot me an email or text me. We can set up a Zoom session too if you want. Okay, new equation. All right, so we got to get rid of this one. That one don't work anymore. Let's see, N2O4 gas decomposes into 2NO2, I'll bet you. Right? Yep. And the K, we'll put it out here away from the equation. 10 to the minus 4. 4 times 10 to the minus 4 is the K. That's equal to NO2 squared over N2O4. Okay. 1 mole sample of N2O4. So initially, 1 mole is introduced into a 10-liter vessel. So that's 1 mole per 10 liter. So that's equal to 0.1 molar, correct? Calculate the equilibrium concentration of both of these. So we have a change and we have an equilibrium. Okay, if this starts off at 0, because this was introduced into the vessel and allowed to come to equilibrium, then that means not given any other information. No. Okay. So it's going to move this way. And in this case, we want concentrations for both of them. So we can pick whichever is easiest to deal with. I think not having fractions is probably easier. This is going to end up here. Excuse me. No. Okay. Minus x here, that means this is plus 2x. Stoichiometry says that when you lose one of these, you get 2 of those. So this would be 0.10 minus x, and this would be 2x. Okay. So if we plug those values in, right, 2x squared over 0.10 minus x equals 4 times 10 to the minus 4. Let's see. Is it just going to give us the answer? Or does it want me to solve it? Oops. Wants me to solve it. Okay. All right. So let's see, this would be 0.1 times this would reduce that to 10 to the minus fifth. And then minus x times this is minus 4.00 times 10 to the minus 4. X equals 4x squared, right? Now, I'll tell you what, this is going to leave us with a quadratic equation. So this is very small. What does that mean? That means that this side is going to be extremely small. Right? If this is a small value, then the product is going to be extremely small, which means that this term, this x, we don't want to eliminate that x as being small because we got to solve for it. But subtracted from 0.1, this value is going to be extremely small. So this is approximately 4x squared over 0.10 if we drop that x out. That's the approximation I was talking about. That way, we actually get 0.1 times this is equal to 4x squared. Now we can solve that pretty easily. So 4 on this side would give us, right, 4 divided on both sides would be 1 times 10 to the minus 5 equals x squared. And x equals a square root of 1 times 10 to the minus 5. That's 3.16 times 10 to the minus 3. That's x. So the concentration would be 0.1 minus this value, correct? So, did I lose anybody? Okay. Well, 2x would be 2 times that. This would be 6.32 times 10 to the minus 3 molar for that concentration. And this one would be 0.1 minus that value. 1 minus is 9.37 times 10 to the minus 2 molar. And let's see what we got. 0.097. Okay, 1, 2. Well, rounding error. And this one is 6.32, 10 plus 3. Let's see if I did that one right. 0.1. Right. Yeah. 0.1 minus x, 3.16 times. Oh, it is 9.7. Why did I get 3.7? I misread it. I got 6.8. So they were right. Okay. Learn how to use ice tables. Get comfortable with them because they're going to stay with us to the end of the semester. We're going to talk equilibrium from now through acids and bases, through formation constants, through solubility products. All are going to use this problem solution method. Oops, before I do that, let's see what's next. Okay, Le Chatelier's principle next. I think I used to have some videos, but I got a nasty email from the creator of the videos. I just took them out. Okay, Le Chatelier's principle. I think there's a at over the A. I didn't understand what that was for even when I was taking French. I just barely understood what the accent grave and accent aigu means. Anybody had French? Yeah, okay. So, yeah, I don't know. I couldn't converse in it now. Okay. So, Le Chatelier's principle. If we have a system at equilibrium and we stress it, and this, I wonder, I should have put a date here somehow. Le Chatelier's principle. I think Le Chatelier preceded Wade and his son-in-law and their mass action equation. I think this preceded them. Le Chatelier just observed that if the reaction is at equilibrium, and we know that from measuring concentrations, and it's at equilibrium, if we stress the system in any way, the system will respond as if it's alive. It'll respond to relieve that stress. Okay? We mentioned one of them earlier when we talked about concentrations. If you increase or decrease the concentration of a reactant or product, the system will respond to replace a removed product or consume an added product until it reaches equilibrium again. Okay, so that's the concentration effect. Oh, I do have.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
The reason I wrote that up on the board is to introduce the concept of coupled reaction. Primary reaction that we're interested in is this one. But, and it's easy to add iron or add thiocyanate and get it to move this way. It's more difficult to add this and get it to move that way. So instead, we try to remove one or the other of these. And one of the ways to do that is couple a reaction that effectively removes this from the primary equation. So we make a hydroxide out of it, it forms a solid. It's no longer part of that available for that reaction. And that reduces it, and you see the shift back this way. And with silver, we did it with the thiocyanate ion to make a solid, and it shifted to the left. Okay. Now what happens? That was concentration. So we can make a list. Stressors, concentration changes. The second one is temperature change. We know that if we change the temperature, we actually change the K. So by changing the K, we shift the equilibrium. Okay, but it depends on whether the reaction is endothermic or exothermic as to whether that shift is to make the K larger or smaller. And the easier way to handle exothermic versus endothermic equations and the effect that temperature has on them is to make temperature or heat a term in the reaction. So I'm going to use the Haber-Bosch equation as to illustrate this point. This is the way we've seen it so far, like this. Okay, but we know this reaction is exothermic. So if it's exothermic, which side would the heat term be on? That side. There's our enthalpy term. Okay, now we can treat it like a term in the equilibrium equation. We don't really put it in the law of mass action because it doesn't have any mass. But if we consider it in terms of Le Chatelier's principle, if we're at equilibrium and we increase the temperature, which way should the equilibrium shift? We add this, goes that way. if with another equation, if we have the heat term on this side and we increase the temperature, it should produce more products and increase the K value. This would decrease the K value because we're decreasing at equilibrium, we're decreasing the ammonia, which is in the numerator. Okay. But if you don't know whether it's endothermic or exothermic, changing the temperature, you may have to either throw up your hands or deduce what you expect to happen. And I think we've got a couple of sample problems that do that. We'll look at those when we come back. Okay, that's the temperature effect. The third effect we consider is pressure. Leave that up there, just in case. The pressure, change the pressure of a reaction mixture. The simplest way to do it is to change the volume. That way, you're not adding anything or subtracting anything from the reaction. You're not introducing concentration problems. But if you change the volume, you are changing the concentration, right? If you decrease the volume, you're increasing the concentration. All right. What effect will that have on the equation, the position of the equilibrium? Only if there are gases, right? That's the first condition. One, you must have gases available in the reaction. And two, unbalanced moles. What I mean by that is, in this one, we have 2 moles formed from 4 moles input. So the total here is 4 moles of gas down to 2 moles of gas. If there's no balance, if the stoichiometry of the equation is unbalanced in gases, then changing the pressure will have an effect. The effect, if you increase the pressure, if pressure increases for this equation, which way is it going to shift? Whatever it takes to relieve that pressure. And we know from our gas laws that relieving the pressure would be reduce the number of moles of gas. So increased pressure would shift to the right in this equation. Decreased pressure would be just the opposite. Shift to the left to produce more moles to fill that space that you've created. If we have an equation where there's same moles on both sides, pressure will have no effect. Or if we, let's see. Yeah, we have the same moles of gas on both sides, changing the pressure has no effect. Or if you change the pressure by adding a term that's not part of the reaction, that pressure change will have no effect. For instance, if we add, say, I don't know, helium, right? We add helium gas, we push it in there, we know that with added moles of gas, we're going to get an increase in pressure. But that pressure will have no effect on the equation because helium is not part of the system. Okay, that's the pressure change.